So, today, when we get into it, I guess we'll talk about dimensional analysis, which is a misnomer because it's really dimensionless analysis, is what we attempt to do, as we'll see later. But it's, I guess this looks like it looks like a DC3 or something, doesn't it? So, in a wind tunnel. So the whole idea is that we spent our time looking at analysis and using Bernoulli and using Reynolds transport theorem. We talked about Navier-Stokes equations. They're all the same thing, but just increasingly more sophisticated as you go along. To be able to, say, make predictions about lift on a plane, and I guess there's lift on this plane because it's just pulled up the back wheel of the tarmac on this model. I presume it's a model. I have no sense of scale, but it would be a hell of a wind tunnel if you get a full plane in, I suppose. Perhaps you can. And it's gone down again. And so the idea is that you can make a full-scale model, or a scale model, not full-scale model, where the dimensions are proportionately changed. And run a flow over it and measure something about it. So what you could measure is you could measure the lift, you could measure the drag for this, and you could, if you were smart about it, if we were smart about it, perhaps you could figure out how to make the conversion between this model forces and the prototype, the forces that would be on a prototype. And of course, if you can measure the force, calculate the forces on a prototype, you can figure out whether you have enough lift to get it off the ground, is basically the idea. So that's kind of our task for this week. Not sure what the other things are. Yeah, this is kind of an interesting one. I think there's a movie attached to it. Not sure what this is. Don't need the sound. But this must be a fossil. No, obviously, we didn't find the dinosaur running around. This is a fossil that's been found of a winged dinosaur, I guess. And again, I guess a question you might ask is whether the appendages on it were for flying or for something else, and whether it can fly. And so I think this is exactly doing the same thing, but instead of building a prototype aircraft, you build I don't know if it's a scale model or whether it's a full-size model of this creature with its appendages. I don't know whether the feathers would have been found. I suppose they were, or whether you have to figure out whether they might have been made up, that if you have a wing that has no feathers on it, you could surmise that it might have some feathers to be able to do something like fly. And ultimately, they're going to use it in a wind tunnel. I guess it'll come to this. I could let you listen to what he's saying, but yeah. Come on. So yeah, so you can see the winds. There's some slight flutter on the end of the left-hand side, the side closer to me, the main wing. And I guess you'd find out what the other things are, whether the rear ones are stabilizers or for steering or what you're doing exactly. And so it's doing exactly the same thing. They're putting it in a wind tunnel. They're measuring the forces that get applied on it in flowing air over it at certain velocities. And from that, you can come to some conclusion as to whether it could fly or not. I guess I should. You'd be able to figure out exactly what it would be. This is interesting as well. Yeah, this is kind of different. This isn't related to anything. Hello. And so this is nothing to do with wind tunnels so much, but I thought it was kind of curious. Seeing whether it would fly across Everest, I guess. Seeing whether these ducks can migrate across the Himalayas. Of course, the Himalayas are tough to get across whether you're in a plane, because they're already at, Everest is 29,000 feet. Planes fly at 30 to 32 to 35 would be quite high. They go higher because the air is less dense and therefore there's less drag, as we'll find out. So there's some economy to going at some height. But I guess the question is whether, if the Himalayas are in direct path of your migration route, how you get around them. I guess you could fly up the valleys rather than across the tops of the mountains. But I think the bizarre thing about this is that they do have them. They train them so they fly actually in a wind tunnel. And not only do they fly in a wind tunnel, obviously the wind tunnel doesn't have any, isn't at 30,000 feet, and therefore doesn't have the density of air that's equivalent to that. But it looks like they have a mask on them, which is tethered with an umbilical behind them. You see the thing on the face. And I think that mask has probably lower dose oxygen on it than air, to be able to simulate whether physiologically, there you go, physiologically they could fly with that amount less air, because obviously that's one feature of Everest. One feature of flying at Everest heights would be that the air is less dense, and therefore you get perhaps less lift for each flap. But secondly, that physiologically you might not be able to deal with it just because of the lack of air. And so I think that's kind of curious. And I'm not sure what the other one is. Is the other one Verrazzano or Tacoma? Yeah. So you've all seen, presumably in your high school physics classes, you'll have seen the classic case of the the first Tacoma Narrows suspension bridge from the 1950s. Only has to happen once, that you design it so that it, even in a steady wind, so the whole thing about this is like a steady wind blowing over a guitar string. And the idea, as we'll see, is that as the wind flows across the deck, as it comes off the leeward side, the downwind side of the deck, if the velocity is just correct, then what it will do is that the flow field will have a vortex that is shed from the top of the deck, and then a little later from the bottom of the deck, and it will alternate. And so this so-called von Karman vortex street, which is shedding vortices alternately from the top of the deck, bridge deck, and the bottom of the bridge deck, gives it a little oomph, which if the resonant frequency of the deck, just like a guitar string that gives you a particular note, is such that that excitation is congruent with the resonant frequency of the deck, then it starts vibrating at that frequency, and the amplitudes get larger and larger, and ultimately it pulls itself to pieces. So I don't know when exactly that happens. So-called galloping Gertie. And of course, I don't have it here, but there's, when you put a new building up in a city, they typically do wind tunnel tests to see what the forces on that new building are due to the buildings around it, and what the forces from that building would be on the buildings that are around it, so that they don't have problems when you build it. And so this is a good thing. So the point being that what we'll talk about today is we'll kind of backtrack from our analysis, and we'll look at ways in which you can do model tests, just like the wind tunnel tests on the airplane to see whether it will lift, the wind tunnel tests on the dinosaur to see what the magnitudes of the forces are. And the whole idea in putting a bridge like this in a model, in a wind tunnel, would be to measure the forces that get applied on it, to measure the resonant frequencies on it. And of course, there's a whole art to be able to make the model just the same as a scaled down prototype. So not only do you have to scale the dimensions, say a 10th scale model or a 100th scale model, every single dimension would be a 100th scale, so it'd look just like the real thing, but at 100th of the size. But you'd have to scale the material properties for this, right? So you'd have to scale the elastic properties in such a way that you'd be able to test them, that the results you'd get from a model test in a wind tunnel would make some sense, and you'd do something with it. So apparently they have two new bridges side by side. They rebuild a bridge, and they have two that are side by side I guess, in the Northwest in Seattle. Tacoma Narrows. All right, so that's what we're up to today. So that's the basic idea. So if I bring this up, and I already mentioned the fact that, so we're got a whole new topic. So dimensional analysis, I said already that it's kind of a misnomer because it's really what we'll work with is what are called non-dimensional numbers. And these numbers are stuff, we talked about them at the very beginning of our class. We talked about them maybe on the second time we met. And these are Reynolds number, Froude number, and Euler number. And so that's where we're going with this. So let's start with a very simple idea, and that is that we can take groupings of parameters that we have in our system, and we can group them together to make life easy for us. And we'll talk about something called Buckingham Pi. That's interesting. I guess that's not the one that I wanted to be drawing on. I was wondering why my page here looked different from what I was looking at. And I don't know, this could be pi or it could be pi. But the idea is that there's a formal way that we can look at things to be able to describe behaviors. And so since on Friday we're talking about Darcy's law and porous media flows, why don't we look at that? So say we had a core, that's not a very good circle, that we had, that we're flowing fluid in. We want to flow fluid through this at some velocity. We can define the behaviors of this relative to some datum. And relative to that datum, I perhaps have drawn it a bit too high up. This is Z0, Z1. And if we do it in green again, just like we did last time, we could draw a pressure upstream and a pressure downstream. Not very well drawn. And this is P0 over unit weight. And this would be P1 over unit weight. And we could draw those together. And we could classify that parameter of these two as head. Head is equal to P over gamma plus elevation. And we can use that to define behavior. And what we found was that we could write an empirical relationship from Henry Darcy, I guess, from the fountains of Dijon, was that the velocity is equal to the hydraulic conductivity times the change in head gradient over a length. And you could either think of dx as being in the x direction horizontally or along the thing. Perhaps we don't really have to worry about it, what it is. And so if we wanted to explore this behavior, we could use this theorem of Buckingham Pi. And it says that if a system is described by, I can't remember what we use in the text, n parameters. And so our n parameters in this are velocity, hydraulic conductivity, meters squared per second, dH and dx, say, which is 4. Occupying, I guess. M physical parameters. And so our M physical parameters will be mass, length, and time, and maybe temperature. In your book they use theta for temperature. Then system is described by n minus m dimensionless parameters. So it's very easy for us to be able to look at that. So in this case, this number for us is 4. This number, well, we'll see in a moment how many this is. So let's look at those parameters. So we have velocity, we have hydraulic conductivity, we have change in head, and we have a length. So this is meters per second. This is meters per second. This is meters, and this is meters. And so what we'll ultimately do is we'll divide these things into mass, length, and time, where you understand what these individuals are. And so velocity is in units of meters per second, so that would be length to the power 1, time to the power minus 1. Hydraulic conductivity, just in case you don't remember what it was, it's kind of equivalent, the coefficient of permeability. It's units of length to the power 1, t to the minus 1. And obviously these are length to the power 1 and length to the power 1. And no time, and for all of them, no mass. Doesn't turn up. So we've got to make a value judgment of this, just these 4 parameters. And so that means that from these 4 parameters, we have length represented, we have time represented, so there's 2 of these. So 4 minus 2 is equal to 2. And so we'd expect to have this system divided into 2 non-dimensional parameters. And actually, take it on trust, but you can see it, the only 2 parameters that we can have, these would be called the pi groups. And they're going to be equal to velocity over permeability, hydraulic conductivity, and could be dH over dx, or the reciprocal of them. But it can only be these 2 because there's no other way that we can combine them in a minimum set to be able to get that. And so what this says is if we want to do some experiments, then we could do some experiments and we could plot dH dx, and we could plot velocity over permeability, hydraulic conductivity. It's a bit contrived because we measure or apply a head. We define an x by the length of our sample. We have a velocity which we measure coming out of it. And this is really not a measured parameter, it's a function of the system. But this is saying that if there are only 2 groups, then these have to be linked in some unique way by some curve. And we know already from Darcy's law that there's a relationship between them, which is v is equal to k dH dx. Which is 1. And so there's a relationship between them. If we had another variable in here, which was, say, the diameter of this tube, flow tube, then we would have, that's called uppercase D, just not to confuse it. It's in units of meters. It would be this. So I'm just adding this. So this would be 5 minus 2, be equal to 3. And so it would say that instead of having just 2 of these non-dimensional parameters, we have another one. So the other one would be something like, you could choose it. It has to be one of these length-only ones. because there's no time in this. So it could be that there's another parameter which is d over dx. And so you could do the experiment with a bunch of different diameter samples, all of the same length, and you could plot the results on this. And of course, changing the diameter of this wouldn't make any difference to the velocity that's coming out of it. And so you'd have a whole bunch of lines for different values of d over dx equals 1, d over dx equals 2, etc. They'd all overplot each other. And so all this theorem does, is one, allow you to choose the units or the parameters that you look at in your experiments. So you do a minimum number of experiments. So for this, if you realize that this scales in this way, you could do one experiment at this particular gradient. You could do one at this particular gradient. And you could do one in the middle. And all of a sudden you'd see that you have 3 data points and looks like it's a straight line. And so you can write Darcy's law from that. And you could surmise that this law exists in some way. And so all that dimensional analysis is by making non-dimensional parameters that allow you to say something about the system. So that's kind of a bit of a hokey way of doing it, but it explains it in a pretty simple way. And of course, we can do this same thing for looking at pipe flow, for looking at flow around objects, and we'll do that. And what we'll see is that these parameters, Reynolds number, Froude number, and Euler number, which we'll talk about, are the important parameters that govern the behavior for flows. But non-dimensional analysis is something you could apply to anything. You could apply it to finance, I suppose, as well, if you wanted to, but we won't. And so what we'll do is we will try and remember a little bit about what we've done. And so what do I want to say? Yeah, okay. Let's go a little trip down memory lane. And that is, so weeks 4 and 5, if you recall, we talked about Bernoulli's equation. Velocity, gravity, pressure, unit weight, and elevation. And we had these other 2 terms, head loss, I'll add to it as well, even though we didn't talk about that, equals constant. Not quite true, right, in some respects. But it was all related to flow in a stream tube. It's kind of one-dimensional flow. So I want to just talk about the things that we've already discussed in the class and see how they fit into these 3 magic numbers that we've talked about at the top of this sheet. And that is that we've done it along a streamline, and we've looked at the total energy gray line of this system has defined this behavior. We looked at, okay. So in week 7, so this obviously is Bernoulli. Actually, this is Bernoulli, but this is the energy equation, which was week number 8, right? Just last week. So if you look at 7, this is the conservation of momentum. And it was sum of the forces in some direction is equal to velocity, I guess sum of velocities times mass flow rates. And we could describe this behavior based on this. And then last week, we talked about what were Navier-Stokes equations. So this is a progression. So this here is no different from Bernoulli, but really for kind of a random geometry, and we always used a geometry that was not so random. I guess we used kind of the vane geometry was perhaps the most unusual geometry that we used for this. So this was conserving mass times velocity. So this, I guess, was no energy loss. In other words, HL equals 0, viscosity, because viscosity equals 0. And the Navier-Stokes equations. We didn't spend much time on them, but just to remind you, in case you've already forgotten, they were these very complicated expressions here that we described in terms of their terms. So let's just write out each of these, not one of each of these terms, and really just describe as to what it represents, because it has a direct analog with Bernoulli. And that is, they come out to be rho times velocity times rate of change of velocity. I'll just write them out, is equal to dp dx. This is pressure, not density, plus rho g, plus viscosity, mu, times second order d2v dx squared. That's kind of paraphrasing it. But each of these, so this is mass times acceleration equals sum of forces. And these sum of forces are pressure. This is gravity or potential, and this is viscosity. And the reason for writing this was that you remember that we took this and we just wrote it on a little cubic volume, which is our differential volume, so that we end up with these differential equations. And all we did was we took the Reynolds transport theorem equations and applied it to this. And this was our PDE that we got out of it. And so we can think of it in terms of, again, Newton's second law, F equals ma. The acceleration term is velocity times rate of change of velocity is times density is momentum, mv. So remember that mass times acceleration is equal to mass times rate of change of velocity with time or space. So that's what this term is. And so this actually is no different from Bernoulli. So Bernoulli would be just the same as this equation above, but I'm going to do something with it, so I'll write it out again. Perhaps I'll write it out in a different color. V squared over 2g is the mass times acceleration term, plus p over gamma, plus z, plus, can't do anything but call it HL, I suppose. And again, I'll write each of these terms out because I'm going to use this. So this is inertia, right? You know that when you're accelerating something, the force you have to apply it is to overcome inertia. This is, again, pressure. This is gravity, I suppose. And this is viscosity. Device battery is low. So these are what those terms represent, and I'm going to use that. And so obviously, so all I'm doing is making the point that everything that we've talked about today has been predicated, actually all the stuff we talked about on statics was also predicated on Newton's second law. Even when we talked about deriving the equations for how pressure changes as you go down in depth, we turned most of the terms off, but it was Newton's second law. When we talked about running across the front of the auditorium accelerating fluids in 4.1, that was that expression for Newton's law. And we used that same expression to derive Bernoulli's equation. So this is the theme that we have going through here. One way for us to rewrite this, obviously each of these terms are in units of length. So what we could do is we could multiply through by unit weight of the fluid times elevation, say. And so if I do that, then that is in newtons per meter cubed per meter for this term here, and multiplied by meters. And so the easiest way to think about this term is these are the forces that we're applying to this per unit volume, right? This goes down to just being 1, obviously. Force per unit volume for each of these terms that do different things. Force per unit volume that gives the gravitational weight, the body weight of the material. Force per unit volume that tries to push it across driving flow by pressure. Force per unit volume that is occasioned by either changing the velocity as you go from one side to the other, and also a change in the body force given by viscosity. And so you could think of that as being drag forces on the top and the bottom of this cube that retard its migration across the system. And so the reason for talking about these is that each of these very important non-dimensional terms that we use are ratios of each of these equivalent forces. So the Reynolds number is the ratio of inertial to viscous forces. Froude number is ratio of inertial to gravitational forces, and the Euler number is ratio of pressure to inertial forces. And so if we look at each of these terms, we already did it on the first time we met. If we take the term for pressure and we take the term for inertia and we divide one by the other, 1 on the top and 2 on the bottom, then we get pressure force over inertia. And that is our, what would it be? It would be pressure over rho g divided by v squared over 2g. Get rid of the g's. We don't care a factor of 2 because it's just, we can choose the number we want. 2 doesn't make any difference to the dimensions, but pressure divided by rho v squared is what we'll refer to as the Euler number. And that is this term here. We don't need to go back to that. But an example of where we've looked at that already, if I draw my diagrams, see if you can remember from my diagram what I'm looking at. This was our San Francisco International Airport, where we looked at the velocity coming out of here and the pressure it applied on here to push it off the runway. Pressure force and inertia force were the two things that we used. So we've already seen that. So an Euler number might be useful for us to be able to calculate the pressures that are applied on the structure. So when we looked at those figures earlier on of wings and airfoils of things in wind tunnels, if we provide the right flow regime and measure the lift force or the drag force that's applied on this, that would be as a kind of Euler number. And so what we'd like to do is be able to have what we'll refer to as dimensional similitude, is that we make the non-dimensional numbers of the model within the wind tunnel equal to the non-dimensional numbers of the prototype, the real-life structure. And if we are able to do that, then we can measure the pressure that we get in the wind tunnel on our model, and we could calculate what the pressure would be in our real system. That's really where we're going with this. So that's the first one. The second one will be the ratio of inertia and gravity. So this one and this one. And so I'm going to do these the right way. So this would be inertia divided by gravity. I guess I could write them as upper and lower. So, and these are just the forces due to these things. So inertia would be v squared over 2g. Gravity would be 1 over z. And this would be equal to v squared over gz. Again, we don't care about this. And if we wanted to, we could take the square root of this whole thing. If this, so we're dividing a length by a length, so by definition, the ratio has to be unitless. And so this would be v over gz square root. And you've seen this before as well. And the place you've seen it before is, if I draw it out, and I use my proper colors, large tank, equation of a free jet, right? V equals 2gh, we called it. Right? So didn't throw out the 2 this time, but this is where you've seen it before. And so inertial to gravity is important for free jets. The other thing it's important to is that if you're designing an America's Cup boat to go really fast, the reason that boats don't go very quickly is because they build up a wave in front of them, and then you have to snowplow that wave away. And so the Froude number, which is this is called, I think that's correct pronunciation, is the ratio of those two. And so if we go up to the top here, it's this one. So we've got the Euler number, the Froude number. And the big daddy of all of them, of course, is the Reynolds number. And so that's a bit more challenging for us because, yeah, I guess I didn't do that. And I'll just write this in, is that this term here is mu v over z squared. So don't ask where this comes from. Z over gamma. Actually, you know where it comes from. Did I mean z over gamma? Yeah, I think I do. So this is this term here is coming from this. This is v, this is mu, and this is some length term squared. Mu v z squared. And so if we do this and keep that just on the screen there, I'm going to go back and do it for Reynolds number is the ratio of inertia to viscosity, viscous losses. So you see where I'm going. And let's see if this works out. So this is Reynolds number, which is inertia to viscosity, or viscous forces. Inertia would be v squared over 2g. Let's see if I've written this out rightly. Divided by mu v z over z squared gamma, rho g. So I'll take gamma out and I'll just write it as rho g. And if we do a reduction on that, I know what I'm looking for, what goes out of it. I guess we lose some gravity. We lose a factor of 2. We lose a z and a z squared. We lose a v and a v squared. So it should be velocity, a length scale, and a density divided by viscosity. Yeah, that's all that's left. And this equals Reynolds number. I guess it's apostrophe, right? Osborne Reynolds name. And I'm trying to think, well, we kind of haven't done anything with viscosities before. So the only thing that I can say that it does look like is at the end of the session last time, we were talking about flow within a pipe. I know that's a bit small. And we're talking about the velocities in this. And that the velocity profile really looks like this parabolic form. And we would assume that it looks like this uniform form. And so the reason, if I blow that up, is that the velocity, if this is velocity on this side here, the velocity at the wall of the pipe goes to 0 is because viscosity physically attaches it to the pipe. And you've done your static examples with that, which kind of have that behavior. But this flowing velocity here at the top and bottom of the pipe is equal to 0 because viscosity is finite. And so this gives us the final term that we want, which is Reynolds number, which is inertial forces to viscous forces and are given by these individual terms. And so the idea in looking at these pictures that we've looked at before, and we can go back to it. Well, why don't we have some time? I'm ahead of the ball here, unusually. We'll go back to this first one. Is if we look at this behavior here. So this is it actually might be a full-size prototype in a wind tunnel. Just looking at the wall behind looks like, you could imagine. Perhaps it's I don't know if it's a scale model or whether it's a full-size model in a huge wind tunnel. But the idea is that you can see that the back wheel of the DC-3 lifts off the ground as you get more lift on the wings. And so the idea would be that you'd measure the forces that are applied on this system and try and convert them to, if it was a full-size model, then you wouldn't have to do anything because it would be the full-size model that you're looking at. But if, I guess, you're looking at the winged dinosaur, which is the other one we looked at. Can we go back to it? I don't really want to see. I don't want that one. So, where is it? 9-1. Yeah, fine. So we looked at this one. Guy looks like Steve Jobs. So here's the idea, is that you put this thing in the wind tunnel. I don't know if this is full size or if this is scaled down, but the idea is it's suspended and it would have some weight to it. And I suppose if you flowed air over the wing, then if it had lift, then it would actually increase the weight, right? It would pull it down. If you'd expect to have lift is by having some kind of force that reduces the pressure on the underside of the wings so that it relatively increases the pressure pushing up on the wings. The dinosaur is upside down in this case, I think, and therefore you could measure the forces that are applied on it and be able to make that connection to be able to do an analysis that would say whether the creature would fly or not. And so if we apply that to our case, then what we're attempting to do is we're attempting to have what we will call similitude. Similarity, if you like. Similitude. And there are three forms of similitude. So they are geometric. And that is that the length of the model is equal to, sorry, not equal to, length of the model to the length of the prototype is constant. So a 100th scale model would be 1/100, right? So You have a dinosaur, perhaps it's a huge dinosaur, you scale it down, so every single dimension on the dinosaur, the depth of the wings, the thickness of the wings, the size of the head, etc., scales down. The second one is called Kinematic Similitude. And that is that the Reynolds number of the model is equal to the Reynolds number of the prototype. And then finally, dynamic. Again, similitude. The top one's similitude as well. And that is that the Euler number of the model is equal to the Euler number of the prototype. And so if you make yourself a model that has the right proportions, the plane that's in the wind tunnel, you run it at a velocity. This really says that the velocity, remember that Reynolds number is equal to a velocity, a density of the fluid, a length scale, a length divided by a viscosity. And so this, you control the fluid that you're flowing in. So these ones of dinosaurs flying in air and planes flying in air, the fluid was air, and so the density between the model and the prototype would be the same, but it doesn't have to be. You could do a wind tunnel, a water tunnel model for an airplane in water, and then use that to calculate the behavior if it was flying in air. Because you can factor out the influence of the viscosity and the density of the different fluid by using this non-dimensional number. So what this means is that if you look at this, I don't know if I've got multiple pictures. No, I don't. And so this is a picture, maybe the Schlieren picture, of fluids going past a pencil, a cylinder in a flow field. And we've talked about flow nets last time, and we used the analog that if you had maybe an airfoil, then maybe the flow lines that we get around that airfoil would look like this. And we could draw some streamlines around it. And we didn't say it last time, but we could make the case that if these were streamlines, then we drew them in black last time as well, we could draw maybe equipotentials which are orthogonal to those. And these equipotentials represent a high pressure, a lower pressure, lower, lower, lower as you go downstream. But I guess the only thing that I really want to bring out here is that these flow lines actually kind of hug the airfoil. And so if we did the behavior of a circle, let me draw a real circle. Oh, fantastic. And we drew flow lines around this cylinder. Then they'd look a bit like this. So you see that they're hugging the form of this cylinder, and the individual stream tubes would look a bit like this, and the equipotentials on those stream tubes would look something like this. Yeah, you get the picture. They'd be orthogonal to them, and they would be like this. But the point in drawing this is that you see that this flow line completely hugs the cylinders it goes through. So this would be at a Reynolds number, which is velocity, density, maybe diameter, over viscosity, less than 2,000. And so the flow pattern around this at less than a Reynolds number of 2000 would be this viscous flow regime where it hugs this shape. If you do it at a faster flow rate, then you'd see that, I'm just going to draw a couple of, I don't know what these these numbers would be. Well, perhaps I'll keep it as red. Then if you do it faster, then it would do this, and then it would separate on the downstream. So this is RE equals 4,000, I don't know. But the point is, as you look at this, this has a completely different flow regime. And so the idea of kinematic similitude is that you want to have the flow regime around your object that's identical to the one which is in its service life. So you don't want to do it for an airplane that has this viscous flow regime if it's really going to be flying and it's going to be in this flow regime. So the whole idea is that you choose your experiments so that you replicate in the wind tunnel the Reynolds number that the plane would see at life, right? So in other words, Reynolds number model equals Reynolds number prototype. So I don't know what those would be, but it would be density, length, velocity over viscosity. And so for each of these, it would be density, length, velocity over viscosity. So if you're doing it in the wind tunnel in air, and you're doing it in the wind tunnel, if you're doing it in the wind tunnel and the plane flies in air, then this and this would be the same. This and this would be the same. And so what you'd have to do would be that the velocity of the model to the velocity of the prototype is equal to the length dimensions, velocity of the model, this is length of the prototype divided by length of the model. So if you're doing it in air, the only things that you have to do is make sure that these two other parameters are congruent for your system between the model and the prototype. And so the length, if you did a 100th scale model, so in other words, what would this be? If this was, the prototype is 100 meters long and your model is 1 meters long, then these would have to be the values that you choose to be at the same Reynolds number, right? So the velocity of the model would be 100 times faster than the velocity of the prototype. That's what you do. And so all you're doing is you're matching the Reynolds number of the model to be the same as the Reynolds number of the wing when it flies in the air. And that means that if you looked at side on at the wing, then this is what you'd see in both cases. It would look like this. It wouldn't look like a creeping flow that goes all the way around it and comes off. It would be at an equivalent Reynolds number. And then if you do that, then you're guaranteed that if you measure the pressures on your model, then you can convert those pressures to the prototype because of this equation here being, what was it? Pressure over density times v squared of the model equals pressure times the density v squared of the prototype. The densities are the same if it's in air. You know the velocities that you're running at in the two different cases to match the Reynolds number. And so you measure this, the pressure in the model, how much force is being applied on the dinosaur wing to make it go, pressure divided by an area. And that gives you the lift that you'd have on the real dinosaur, and you could figure out whether that lift is enough to carry the weight of the dinosaur. So it's an incredibly powerful technique. And so that's all it is. You have to match it in these three ways. The model has to be at scale in every aspect, every dimension. It has to satisfy kinematic similitude in that the flow regime around the model has to be the same between the model and the real live structure. And if you're then for running at the same Reynolds number, you can measure the Euler number, the pressure that's applied on the model, pushing the building over, or pushing the bridge over, or lifting the airplane wing. And then you can convert that model pressure to what it would be on the full-size prototype to be able to see if it can lift 300 passengers sitting and drinking their Manhattans while you take off. That's it. And so this, you can see kind of a fledgling of what happened when we talked about the Tacoma Narrows Bridge. So if you imagine this being, I probably can't do it. Actually, I think this was a blunt object, was it? One of these was a blunt object. Or perhaps I converted it back. If you imagine the bridge deck for the Tacoma Narrows Bridge as being a box girder that looks like this, that you have air flowing over and under. Then if it's a creeping flow like this at a very low Reynolds number, then it just hugs this and it goes off. If it's a faster flow like this, then you see that this is releasing, you can see it on this figure here, it's released a vortex right here. There's another vortex which is further downstream, and it wants to release another one from the top. So what it's going to do is it's alternately going to release a vortex here. It's then going to release a vortex here, and these all get carried down in what we referred to as a vortex street. So it's a von Karman vortex street. Not sheet, but street. Because it's going down here and it's alternately popping one off the top, then one off the bottom. So what it does is it excites the bridge like plucking a guitar string. And if we still have this one up here, then it does all the things that you'd expect to see from galloping Gertie. And so it doesn't need a high wind. It just needs a wind that gives you this plucking of the shedding of the vortices from the top and the bottom that just happens to be in exactly the resonant frequency of the structure. In other words, the tone you get from a risk life for dog in car, upstaged by a dog in a car. So it just has to be exactly the right forcing frequency that it puts it in motion. And so it sheds one off the top, one off the bottom of it, and it builds the forces. The amplitude slowly builds as you keep on adding energy into the bridge, and then ultimately at some stage, well, you know the outcome of this is that it pulls itself apart. And so you only do that once, and now you know exactly what it does. And so to counter it, you change the resonant frequency of the bridge. And so you could do that by damping it out on supports. You could make the bridge a different weight. You could put viscous dampers in so it doesn't move. So, you know, one of the solutions to earthquakes on buildings is to have base isolation things, which are kind of viscous blocks of rubber, so that when the ground shakes, the building tries to shake at that velocity, but these viscous rubber things change the frequency of the earthquake and allow some of that energy to be eaten up before it goes into the building and shakes the building to pieces. And so that's what we're talking about. So the bottom line today is we can define, do dimensional analysis. There's a formal way of doing it. It's called Buckingham Pi. It allows us to get non-dimensional parameters. We can say from the array of parameters like velocity, density, viscosity, exactly how many of those non-dimensional parameters will govern the behavior of our system. And then we can use that as a very powerful way to do experiments. To one, define the minimum number of experiments we need to do to understand a system, and then we can do the experiments and use geometric similitude, kinematic similitude, where the flow patterns look the same as they do around the real structure, and dynamic similitude to be able to get the forces that are applied on those structures. And that's it. So we'll spend the next 2 sessions looking at some examples to do exactly that. Okay.